Okay, dear students, in this lecture, we'll continue some more parameters of half-wave rectifier. So we will be discussing in this lecture RMS AC output current. So probably it is the parameter number 4 and it is RMS AC output current. RMS value of AC output current is in the half-wave rectifier. Now, the output of a half-wave rectifier or a full-wave rectifier, it is a combination of both AC as well as DC values, combination of DC and AC component. So if we have the output, for example, of a rectifier, for example, this is the current of the rectifier. This is I rectifier, current of a rectifier. So it consists both values, both AC and DC value. So it will have some DC value and then it will also have some AC value. For example, there will be a sinusoidal output, for example, more or less, okay? Although the rectifiers have a constant DC voltage, but if there are certain AC components, more ripples are present, unwanted AC components are there, then it will be more or less, it will not be constant, it will have some kind of variation. So I have made in this diagram, variations are quite prominent, okay? And suppose this is the conduction angle. This is the conduction angle alpha. Alpha is the conduction angle. So for one cycle of AC, we have this kind of output, okay? And we know that it has both AC as well as DC component. So maybe practically the output could be like this. The output could be like this. So you have ripples, smaller ripples. Okay? That is also possible. But this diagram shows for alpha equal to 2 pi, which is full cycle. Okay? So therefore, we can say that our output rectified current, it will be having both DC component as well as AC component. Okay, AC component. And as far as AC component is concerned, we can say I is made up of IDC, and let us say that AC component of the current, rectified current, is represented by I dash. Okay, it is represented by I dash, and let's call this equation as equation 1. We can then say that AC component of the current in the rectifier is equal to I minus IDC. Okay, I minus IDC, which is the total current minus DC component. So this equation will give us amount of AC component of output current. AC component of output current. Okay, and we know that we can then find out RMS value of this AC component. Suppose I dash RMS is the RMS value of this AC component, that is I dash. What is I dash? It is AC component. It is AC component. Okay, and we know the RMS value is always calculated by root of 1 by 2 pi 0 integration 0 to 2 pi, then AC component square d alpha, whereas alpha is the conduction angle in the rectifier. Okay, and if we take the square of I dash RMS, we can say that I dash RMS whole square, it is equal to 1 by 2 pi integral of 0 to 2 pi, then instead of I dash square, because I dash is equal to I minus I dc. So we can write down I minus I dc whole square d alpha. Okay, so we are basically using equation 1. So from equation 1 we are substituting the value of I dash, and we'll be having this thing now. Now we can expand I minus I dc whole square. So we'll be having this thing 1 by 2 pi integral of 0 to 2 pi, then uh, expanding the inner term I minus I dc whole square, we will have I square plus I dc square minus twice I dc into I d alpha. Okay, so this will be d alpha, and this will be equal to 1 by 2 pi, 1 by 2 pi. Then we can give this integral separately to each term, and we will have then integral of 0 to 2 pi I square d alpha plus 0 to 2 pi I dc square d alpha minus integral of 0 to 2 pi twice I dc into I, then d alpha. Okay, so into d alpha. So in the final integral here, this will be all equal to I dash Rms whole square. And in this interval, in this entire final integral, we will have three terms. Okay, we will have three terms. So one term is term number 1, another is term number 2, then we have a third term here, which is term number 3. Okay, so let us first okay, all right. So we have three different terms. So let's expand first term now. Okay, expanding first term. Expanding or solving first term. So what is first term? The first term, we have first term as all right. So we have three different terms, and if we expand them further, we will be able to find that. Let's not expand this first term here. We'll be having I dash Rms whole square will be equal to 1 by 2 pi 0 to 2 pi. Then we have I dash square I square d alpha plus 1 by 2 pi 0 to 2 pi. We'll have another term. So we have there I dc square d alpha. Then the third term will be equal to minus 1 by 2 pi integral 0 to 2 pi twice I dc into I d of alpha. Okay, d of alpha, d of alpha. Now see, we know that we already have discussed this thing in our previous parameters, in our previous lecture. We know that IRMS, it is equal to 1 by 2 pi. We can calculate the RMS value of any quantity. For example, current, it is equal to 1 by 2 pi 0 to 2 pi integration of I square d alpha. Okay, therefore IRMS whole square, we can rearrange this equation. This equation can be rearranged, and then we'll be able to find IRMS whole square will be equal to 1 by 2 pi 0 to 2 pi I square d alpha. Okay, I square d alpha. Then we can write down from first term. Okay, so we have first term here, we have second term here, then we have third term here. So we can write down for first term. Solving or simplifying first term, Therefore, since the first term is equal to 1 by 2 pi integral 0 to 2 pi, then it is I square d alpha. We can write it down, it is equal to Irms whole square, Irms whole square. And that is first term. Okay, it is the first term. Now about second term, we know our second term, simplifying second term, Our second term is equal to 1 by 2 pi integral 0 to 2 pi I dc square d alpha, So this is our second term, okay? And it can be simplified as, because from this IDC is constant, because we are concerned in this parameter about the AC component of the current, RMS value of AC component. So IDC will not be integrated. So IDC will be constant. So we'll take IDC square out. That will be taken out. And we are left inside with 0 to 2 pi. Then we have 1 into d alpha. 1 into d alpha. Once we simplify this integral, we'll be able to find that we'll have 1 by 2 pi IDC square into 2 pi, which will be equal to I dc square. So finally, for second term, we can replace second term by I dc square, okay? Now for third term, we can simplify third term also. Simplifying third term. Now, the third term that we have there in our general equation, it is 1 by 2 pi 2 times 0 to 2 pi. Then we have I dc into I d alpha, okay, d alpha. So we can solve this, or we can simplify this term as, so it will be equal to, because IDC is now here also constant, IDC will be taken out, so it will be twice IDC by 2 pi integration 0 to 2 pi. Then you have ID alpha, okay? Say for example, this is equation A. This is equation A. This is our equation A. We also know that IDC we have already calculated in our previous parameters, in our previous lecture. IDC of a rectifier, it is equal to 1 by 2 pi into integration of 0 to 2 pi I d alpha. Therefore, from equation A, what can we have now? So from equation A, our equation A will be reduced to 2 into IDC into 1 by 2 alpha, or 2 pi, 0 to 2 pi, integration of 0 to 2 pi ID alpha, okay? And instead of this term, we can write down IDC. So therefore, this will be further reduced to twice IDC into IDC. So the third term is reduced to twice I dc square. So this is our third term. This is our third term in equation second. Okay, in our equation second. So where is our equation second? Say for example, this is my equation 2. This is my equation 2. Okay. Now equation 2 can be written, it can be rearranged now. So we can write down now. Therefore, equation 2 can be written as I dash Rms whole square, it is equal to I Rms square plus second term is IDC square minus twice IDC whole square. Okay. So I dash RMS will be then equal to uh, root of IRMS square minus IDC square. So this is the RMS value of AC component of current. Whereas we'll write it down. I dash RMS is AC output current, and this I dash RMS, this is also the reading of AC ammeter. AC ammeter. Okay. Whereas IDC is the reading of IDC is reading of DC ammeter. DC ammeter. So this is the RMS value of our current. Okay, RMS value of our current. The next parameter that we'll discuss is the next parameter will be let's write it down. Let's continue it here. 5. The next parameter is ripple factor. Ripple factor, which is denoted by small r, ripple factor. Okay. So ripple factor basically is a measure of ripple factor is a measure of amount of ripples or AC component present in our output. Okay. So what are the ripples? So ripple factor is a measure of amount of ripples or AC component present in our output. Ripples are the unwanted AC components present at the output of the rectifier. At the output of the rectifier. Okay, at the output of the rectifier. So ideally, our rectifiers should have no AC component present in the output. Okay, ideally speaking, no AC component should be present in output. Okay, as AC component is unwanted, therefore ripple factor should be smaller. Ideally, it should be 0. So since no AC component should be present at the output, ideally speaking, ripple factor should be equal to 0. This is the ideal value. Okay, ideally ripple factor should be equal to 0. Practically, ripple factor must be as small as possible. as small as possible. Okay. And mathematically, how do we calculate the ripple factor? Mathematically, we calculate ripple factor as R. R is the ripple factor, is equal to Rms value of AC component that we just calculated, value of AC component divided by DC component. Okay, so ripple factor will be equal to I dash RMS that we just calculated, I dash RMS divided by what is the DC component, IDC. Or if we are calculating it from voltage values, it will be V dash RMS divided by PDC. Okay, so ripple factor in terms of current, it will be equal to what is I dash RMS equal to? It is equal to root of I RMS square minus IDC square divided by IDC. If we simplify it, it will be equal to root of IRMS square divided by IDC square. So we'll take whole square, okay, minus 1. And ripple factor will be then equal to what is RMS value? RMS value of current is also equal to Im by 2. We have calculated it in our previous lecture. Okay, please go back to our previous lecture. You'll be able to find out the RMS value of current is equal to by Im by 2, and DC current is equal to Im by pi and whole square. Then you have whole square minus 1. So it will be finally reduced to pi by 2 whole square minus 1 minus 1. So for half-wave rectifier, ripple factor is equal to pi by 2 whole square minus 1. And once we substitute the value of pi and in this equation, we'll be able to find that for half-wave rectifier, ripple factor is equal to 1.21. 1.21. So therefore the output, we can say that, therefore the output of half-wave rectifier has greater AC component present in it, which is a drawback. So it is not fit for a DC power supply. It is not suitable one for a pure DC power supply. Why? Because it has a very high AC component present in that. Okay, present in it. Now the next will be the next parameter is input power, which is P of I. What is input power? Input power is defined as it is the average value of product of instantaneous voltage across secondary winding and instantaneous current through the secondary winding. Okay. Now see, power is always equal to voltage into current, product of voltage into current. As far as rectifier is concerned, or a power supply is concerned, you have something like this. You have a step-down transformer generally. So this is a step-down transformer. So somewhere we have an AC power supply of 220 volt AC. We are operating in India, and we know this is the primary side of the transformer, and this is the secondary side of the transformer. Okay, and this is our step down transformer in the rectifier supply or in the power supply. This is step down transformer. Okay, and the next stage immediately after the step down transformer is our rectifier. It is our rectifier. Okay, rectifier. Now see, for the rectifier, what is the input to the rectifier? This is the input voltage. So input to the rectifier is output of the secondary voltage. So Vs. Vs is the input to the rectifier. And what is input current to the rectifier? It is secondary current. That is why we said that it is the average value of product of instantaneous voltage across secondary winding, that is the secondary voltage, and instantaneous current through the secondary winding, that is secondary current. So input power is basically, it is average of Vs into I of S, because this is the input side to rectifier. Input side to rectifier, okay, and this is our output side, input side to rectifier. So power, input power will be measured from this side. Input power will be measured from this side. So what is input power equal to? It is average value of Vs Is. Basically, it is average value of input voltage into input current. Okay, what is input voltage? Vs here. Okay, so we have, which is V input also. This is I input also. Is I input. So Pi, input power, average power, average value of a quantity, it is measured by 1 by 2 pi integration 0 to 2 pi, because we are taking one cycle into consideration. One cycle, okay? So we are taking one cycle of AC waveform into consideration. So it is from 0 to 2 pi. So that's why we are integrating from 0 to 2 pi. Then it is V of I into I of I. And then it is D alpha. V of I into I of I. Okay? V of I into I of I. V of I into I of I. Now, see, if we expand this transformer circuit here, we can write down this circuit can be represented as this. We can simplify this rectifier circuit, basically half-wave rectifier circuit, and this transformer. Now see, secondary of transformer, the circuit is for half-wave rectifier. The circuit with step-down transformer is something like this. You have a diode here, then we have load resistor. Okay, we have load resistor, and this is our secondary winding, and this is our primary winding. So this is the circuit for our half-wave rectifier, and you have a diode D here, and we can its equivalent circuit would be uh, an inductor. This is the secondary winding. Then instead of diode, we will replace it by the forward resistance of the diode. Then we have a load resistor here, R of L. Okay, R of L. So whatever is present between these 2 points, this will be input to the rectifier, because this is input here. This is your V input. So V input is here between points A and B. Okay, so V input. And whatever current will flow through the circuit, say for example, it is I is the current that flows through the circuit. Then we can say that we applying KVL in the circuit, we can say that V of I, it is equal to I into R of F plus R of L. Okay, so Vi will be equal to IRF plus IRL. Okay, IRL. So this IRL is basically a voltage drop across here, and IRF is basically voltage drop across diode, and then we have Vi is basically your input voltage that is present somewhere here. So therefore we can write down uh, P input is equal to 1 by 2 pi integral 0 to 2 pi Vi into I input d alpha. Okay, d alpha. And this can be written as integration 0 to 2 pi Vi into what is I of I? I of I is I, because here in this circuit we have current I. Okay, so it is I. Then you have d of alpha, and instead of Vi, for example, this is equation B here. Instead of Vi, we can write down I into Rf plus RL. So we can write down this will be then written as Pi will be equal to integration 0 to 2 pi. Instead of Vi, we will use equation B. It will be I into Rf plus RL into I d alpha using equation P. Okay, so it will be equal to Pi. So Pi will be equal to 1 by 2 pi 0 to 2 pi. Then you have uh, okay, 1 by 2 pi. Rf plus RL are constant. They will be taken out. And inside we will be left with 0 to 2 pi integration I square d alpha. Okay. Or we can say that Pi will be equal to P of I input power will be equal to Rf plus RL into 1 divided by 2 pi integration 0 to 2 pi I square d alpha. Now see, we have already explained this term in our previous parameters, that this term will boil down to I square Rms. So input power of half-wave rectifier is equal to Rf plus RL into I square Rms. This is the input power of the rectifier. Okay, input power of the rectifier, or input power to the rectifier. The next parameter that we'll discuss is efficiency. So parameter number 7, it is efficiency, which is represented by neta. Okay, efficiency is represented by neta. Now efficiency is a measure of the ability of a rectifier to convert input AC power into DC power. Okay, so mathematically neta, what is neta? Neta is equal to DC output power divided by AC input power. So mathematically, the efficiency will be output by input. Output of a rectifier output is DC. And its input is always AC. So it is DC by AC, because efficiency is always output by input. So it is DC output power divided by AC input power. AC input power we have already calculated, and PDC we already know. Okay. So in terms of percentage, it will be PDC divided by PAC, or which is P input power, okay, into 100, and that will be efficiency in percents. What is PDC equal to? PDC is, now see, power is equal to I square into R. Power delivered to the load is current square, load current square into load resistance square. Okay, so we can say then output power is equal to, what is the output load current? It is DC current. So I square DC into R of L divided by, what is AC input power equal to? It is RF plus RL into I square RMS into 100 into 100, okay, into 100. And IDC, we know it is equal to Im by pi whole square into RL divided by RF plus RL. And what is IRMS equal to? IRMS is equal to Im by pi, Im by 2 whole square, whole square into 100 into 100. And this will be then Im square by pi square divided by Im square by 4 into RL divided by RF plus RL into 100 into 100, and that will be equal to 400 divided by pi square into RL divided by RF plus RL percents. Okay, so this efficiency is in percents. Now see, assuming that, if we assume that the forward resistance of the diode is very small, it is very small, few ohms, okay, few ohms, very small. Therefore we can neglect RF can be neglected then, and substituting values of value of pi in equation, say for example 6 we have. So what will we obtain then? We'll obtain the percent efficiency will be equal to 400 divided by pi square. Okay, pi square we have to substitute the value, but RF has to be neglected. So RL divided by RF will be equal to 0. Okay, it will be 0 plus RL. It will be RL. So this is percent. So once we substitute the value of pi in the equation, we will be able to find that efficiency of the half wave rectifier, it is equal to 40.5. Okay, so it is equal to 40.5, and which is the maximum efficiency of half wave rectifier, maximum efficiency of half wave rectifier. I'll stop here and I'll continue with more parameters in my next lecture.